Hello and welcome to Solved, where we help you solve problems. In this video, we will be analyzing the solution to the energy balance of a two-step process. Here's the problem. Liquid benzene at 25 degrees Celsius and 1.2 bar is converted to vapor at 200 degrees Celsius and 5 bar in a two-step steady flow process. First, compression by a pump with an efficiency of 70% to 5 bar, followed by vaporization in a counterflow heat exchanger. We want to determine the duty of the heat exchanger and the power requirements of the pump. Let's go ahead and solve that problem. This is the illustration of our problem. We have a two-step process. First, we have a pump, and second, we have a heat exchanger. The purpose of the pump is to increase the pressure of the liquid benzene, that is from 1.2 bar to 5 bars. Of course, that occurs with the input of shaft work. For the second process, we are heating the benzene such that it turns from liquid to vapor at constant pressure. We know that the temperature of the outlet is 200 degrees Celsius. That is, of course, with the addition of heat to the heat exchanger, presumably with the use of a heat exchange fluid. We are required to solve for the heat exchanger duty, which is simply the rate of heat transfer provided to vaporize our benzene. And second, we need to determine the power requirement of the pump, which is the rate of transfer of shaft work. Let us start with the power requirement of the pump, because that allows us to set our system boundary to just the pump. Considering boundary A, our general energy equation is written as the mass flow rate of liquid benzene multiplied by delta H plus the change in kinetic energy plus the change in potential energy is equal to the rate of heat transfer plus the rate of shaft work transfer. We can assume several things about this pump, and our best guess is the pump operates adiabatically such that the rate of heat transfer in the pump is equal to 0. Keep in mind that the rate of heat transfer is different in the pump and it's different in the heat exchanger. We are simply considering the pump in this instance. Also, we can assume that the change in potential energy is negligible, as well as the change in kinetic energy because there were no given velocities or elevations in this example. Therefore, we are left with the rate of shaft work transfer is equal to the mass flow rate multiplied by the change in enthalpy. Another safe assumption that we can make here is that the pumping process is isothermal, such that all of the input shaft work is provided to increase the pressure of the liquid. Therefore, we can rewrite our equation to become the mass flow rate multiplied by the specific volume of benzene multiplied by delta P, or the change in pressure of benzene. Keep in mind that this equation is only possible if we assume that the pumping is isothermal and that benzene is incompressible such that its specific volume is constant. This also suits the given in our problem because we are already given delta P. We know that the initial pressure is 1.2 bar and the final pressure is 5 bar. All that's left for us to do is to estimate the value of the specific volume of liquid benzene. For this part, we only need to get the ratio between the molecular weight of benzene and the density of benzene. This expression will give us the units cubic meters per mole if the molecular weight is in kilograms per mole and the density is in kilograms per cubic meter. The molecular weight of benzene is 0.07812 kilograms per mole, and the density of liquid benzene at 25 degrees Celsius is 879 kilograms per cubic meter. That gives us a specific volume of 8.89 times 10 raised to negative 5 cubic meters per mole. This is for liquid benzene. We can now substitute this value to our expression for the rate of shaft work. However, in this problem, we are not given a mass flow rate. So the best thing that we can do to determine the power requirement of the pump is to determine the specific shaft work. That is, the ratio of the rate of shaft work transfer and the mass flow rate. That is simply the specific volume multiplied by P2 minus P1. The units of specific work are in joules per kilogram. That means that whenever we are given a value of the mass flow rate, we simply multiply the mass flow rate to our specific work in order for that to be turned to the power requirements of the pump. Substituting, we have here the specific volume of liquid benzene in cubic meters per mole, and we simply multiply that to the difference in pressure. That is 5 times 10 raised to 5 to convert bars to pascals, minus 1.2 times 10 raised to 5 pascals. Our specific shaft work is equal to 33.77 joules per mole. Now we have to be careful because this specific work that we have solved is the ideal amount of work that is being delivered to the pump. Remember that we are given a value of the efficiency and that is 70% efficient. Therefore, to get the actual specific work, we have to divide our ideal work with the efficiency. So dividing this with 0.7, our actual specific work is 48.25 joules per mole. Of course, you can always convert the value of the specific work to convey energy per mass instead of energy per mole. But for now, our units of joules per mole would be sufficient for this problem. Let's proceed with the determination of the heat exchanger duty. For the second part of our analysis, we will set our boundary to the heat exchanger. I'm calling this boundary B. And for boundary B, we can write a separate first law analysis. Our general energy balance, in this case, is mass flow rates or molar flow rates multiplied by delta H plus delta KE plus delta potential energy is equal to the rate of heat transfer plus the rate of shaft work transfer. We are now pertaining to the heat exchanger, so therefore there is no shaft work transfer. We are assuming potential energy to be negligible as well as kinetic energies. We will be left with the expression the heat exchanger duty or the rate of heat transfer is equal to the mass flow rate multiplied by delta H or the change in enthalpy. Again, since there is no provided value of the mass flow rate, we will make do with the specific heat transfer. That is Q is equal to delta H. Delta H in this case is H3 minus H2. That's the enthalpy of stream 3 minus the enthalpy of stream 2. For the determinations of these enthalpies, we simply write our general formula as the enthalpy is equal to the heat capacity multiplied by the temperature at a particular stream minus the reference temperature. Again, there is no absolute value of enthalpy. They are always measured against a reference value of the temperature. This expression here is only for sensible heat changes. For latent heat changes, we have to add another term here, and that is the enthalpy of vaporization. In our case, we need to add the enthalpy of vaporization because benzene is transformed from liquid to vapor in the heat exchanger. The only thing that is concerning here is we do not know the saturation temperature of benzene at a pressure of 5 bar. That is because at the saturation temperature, we will be sure that the saturated liquid will be transformed to saturated vapor with the enthalpy change equal to the latent heat of vaporization of benzene. Let us first look for the saturation temperature of benzene. For that, we need to use the Antoine equation. If you remember, the Antoine equation can give us two things. Either it gives us the saturation pressure if we give it the temperature, or it gives us the saturation temperature if we give it the pressure. In our case, we can give it the pressure of 5 bar and it will give us the saturation temperature of benzene at that pressure. For that, let us consult the book Introduction to Chemical Engineering Thermodynamics by Smith and Van Ness. This is Appendix B, Properties of Pure Species. In this table, we will see the constants for the Antoine equation for the determination of the vapor pressure of pure species. The Antoine equation can also be used to determine the saturation pressure or the saturation temperature given either the temperature or the pressure. This is the form of the Antoine equation, that is the natural logarithm of the saturation pressure in kilopascals is equal to A minus B over T plus C. T here is our temperature in degrees Celsius. A, B, and C are all constants. So for benzene, we have here the values of A, B, and C. You simply have to substitute them to the Antoine equation. And for the saturation pressure, we substitute 500 kilopascals. That is the equivalent of 5 bars given in our problem. Solving for the temperature, that is B. The B for benzene is 2726.81 over A, 13.7819 minus the natural logarithm of our pressure in kilopascals, 500. And that ratio is subtracted with the value of C, 217.572. our saturation temperature is 142.8 degrees Celsius. Now, you might have noticed that this saturation temperature is outside of the normal temperature range for benzene. That is okay because again, we are simply approximating the saturation temperature of benzene. Going back to the board, if our saturation temperature is equal to 142.8 degrees Celsius, we can now write our expression for H3 and H2. Remember that H2 pertains to the enthalpy of liquid benzene, while H3 pertains to the enthalpy of vapor or gaseous benzene. To help us defining the enthalpies of the two streams, we need to set our reference temperature. This is the temperature at which all of the enthalpy measurements are based upon. And for our case, it will be easy for us to set the reference temperature to 25 degrees Celsius. That's because previously, we have assumed the operation of the pump to be isothermal such that the temperature at stream 2 is also equal to 25 degrees Celsius. By setting our reference temperature to 25 degrees Celsius, we can already cancel the value of H2. That is because H2 will be equal to the heat capacity of liquid benzene multiplied by T2 minus the reference temperature. Since the reference temperature is equal to the temperature of stream 2, this will be 0. Therefore, enthalpy 2 is 0. Our simplified expression for the specific heat transfer would then be only equal to H3. And we write our H3 as Cp of benzene liquid multiplied by the saturation temperature minus the reference temperature. The first term we have written here pertains to the enthalpy gain of the benzene stream in its liquid form. That's why the temperature range is from the reference temperature 25 degrees Celsius up to its saturation temperature of 142.8 degrees Celsius. This is for the liquid benzene. From this, we add our enthalpy of vaporization of benzene. This is for the transition from saturated liquid to saturated vapor. And then finally, we have the Cp of vapor benzene multiplied by the temperature of stream 3 minus the saturation temperature. Again, to recap, our specific heat transfer composes of three terms because it takes 3 steps for benzene to be converted from a liquid at 25 degrees Celsius to a vapor at 200 degrees Celsius. The first is from 25 degrees Celsius to the saturation temperature to make it a saturated liquid. The second is from the conversion of the saturated liquid to a saturated vapor at a constant temperature. And the final term is from the conversion of the saturated vapor at 142.8 degrees Celsius up to the temperature of 200 degrees Celsius, which is the outputs of the heat exchanger. Okay, you have to be very careful in accounting for all of the enthalpy terms. With our developed equation, we have to look for the values of 3 parameters. First, the heat capacity of liquid benzene. Second is the enthalpy of vaporization of benzene at the saturation temperature. And finally, we also have to look for the heat capacity of benzene as a vapor. From property tables, we can estimate the value of the heat capacity of liquid and heat capacity of vapor benzene, but we have to estimate them at the average temperature values. For the liquid, that is the average between 25 degrees Celsius and 142.8 degrees Celsius. In kelvins, that is 537 Kelvin. And the value of the heat capacity of the liquid at that temperature is 149 joules per mole per Kelvin. We are sticking with the units joules per mole per Kelvin because in our previous analysis, we have determined that the specific work is in joules per mole. Okay, so let's continue to use the molar units. If you're not comfortable with molar units, you can simply convert this to mass units. Next, for the heat capacity of the vapor, we have to determine this at the average temperature between 200 degrees Celsius and 142.8 degrees Celsius. In Kelvin, that is 444.5 kelvins. And the value of the heat capacity at that temperature is 126 joules per mole per Kelvin. The final value that we have to estimate is the enthalpy of vaporization. Now, the enthalpy of vaporization is dependent on the value of the temperature. If we go back to the appendices of the book of Smith and Van Ness, we can see here that benzene has a value of the enthalpy of vaporization as 30.72 kilojoules per mole, but this is at the normal boiling point. The normal boiling point of benzene is 80 degrees Celsius. Remember that we are estimating our enthalpy of vaporization at a higher 142.8 degrees Celsius. That is our saturation temperature. Therefore, we have to apply a conversion to change the values. For this, we can use either the Clausius-Clapeyron equation or Watson's equation. We are going to use Watson's equation since it is more straightforward. Here is one form of the Watson's equation, and we have also determined the critical temperature of benzene to be 562.2 Kelvin. Converting that to degrees Celsius, that is 562.2 minus 273.15. That is 289.05 degrees Celsius. Now for Watson's equation, enthalpy 2 is the new enthalpy of vaporization at a temperature of T2 or at the new saturation temperature. Delta HV1 can be the value of the enthalpy of vaporization at the normal boiling point. That is paired with T1 as the normal boiling temperature. Therefore, our T1 is 80 degrees Celsius. Our T2 is our saturation temperature, 142.8 degrees Celsius. And then we can solve for delta HV2. The normal enthalpy of vaporization, 30.72 kilojoules per mole, multiplied by the ratio, critical temperature, 289.05, minus our saturation temperature, 142.8 degrees Celsius, divided by 289.05, minus the normal boiling point of benzene, 80 degrees Celsius, that is raised to 0.38. Our new enthalpy of vaporization is 26.82 kilojoules per mole. This is now our enthalpy of vaporization at 142.8 degrees Celsius or our saturation temperature. Now we have the values of the three parameters that we need to solve our equation. We can now substitute this back to our equation to determine the duty of the heat exchanger. Substituting on the first term of the enthalpy, we have the enthalpy of the liquid, that is 149 joules per mole per Kelvin, multiplied by saturation temperature, 142.8 minus reference temperature, 25, plus our adjusted value of the enthalpy of vaporization, that is 26,820 joules per mole. Remember that our value obtained earlier was in kilojoules per mole, so don't forget to convert. Plus, for the final term, we have the enthalpy of the vapor on average is 126 joules per mole per Kelvin, multiplied by T3, 200, minus the saturation temperature, 142.8. The result of that is the duty of the heat exchanger, that is 51.58 kilojoules per mole. This is the amount of heat that needs to be added to the heat exchanger in order for us to carry on the vaporization of benzene at the specified inlet and outlet conditions. Okay, again, this is the value of specific heat transfer, and in order to convert this to a rate of heat transfer, we simply multiply this to the molar flow rate of benzene if it is given. Comparing the magnitudes of the specific work being provided for the pump and the specific amount of heat transfer being provided for the heat exchanger, the heat exchanger uses much more energy compared to the pump. That is because the heat exchanger needs to carry out a phase change while the pump is merely increasing the pressure of the liquid. Okay? With these types of analysis, it is hoped that you would now be able to handle multiple steps of open steady-state systems. That's it for this video. Thank you for listening and consider this problem solved.